Great. Well, thank you everyone for attending M.Plan International's third webinar in our 2020 CEO and CFO Webinar Series. Today is the Americas and EMA session, and tomorrow we'll be holding the same conference and for EMA and Asia Pacific, like we normally do. We normally hold two. So I'm welcomed today by my fellow experts, Dr. Sebastian Prinz, who's the Business Development Director at Dorfner ANZAPLAN. And I also have joined by Dr. Christian Graf, who is the Process Division Director at Dorfner ANZAPLAN as well. So welcome everyone, and we'll leave the introductions to when you gentlemen start your presentations. And just a few words before we start. There is a dialogue box for questions, and so please feel free to write if you have any questions. And what we'll do is we'll hold them to the end, and we'll leave time to answer any of those at that point. But this way allow us to timely go through our presentations. So with that, so let's get started. And let's just jump in. And so the focus of today is specifically on lithium. But today I just wanted to start by telling you a little bit about the companies. Here is our disclaimer. Oops. Sorry. Just take a few minutes to take a look at the disclaimer. And on the right here, the picture, there's a nice picture of a lithium deposit, open pit deposit. All right. So to tell you a little bit about M.Plan International, we're a full service provider of specialty minerals and metals, as well as high value industrial minerals. And we work with clients on the project development study side when we're doing PEAs, PFSs, and feasibility studies. We also work with the investment community doing due diligence on projects, as well as acting as lenders, independent engineer during the construction phase of projects. And our services allow us to go all the way from the initial prospect in the ground all the way through to the final product specifications. So that's exploration, mineral resources and reserves, process development, engineering, environmental and social aspects, market intelligence, economic analysis. So we cover every aspect through that project development path. M.Plan was founded in 2015 and is a combination of globally recognized names, Micon International and Dorfner ANZAPLAN. And collectively, we have over 50 consultants worldwide within the business. And just to tell you a little bit about the companies, so Micon International has been in the business for in excess of 30 years. If anyone's done any due diligence out there, they've probably seen the Micon name. They located in the out of Toronto headquartered, as well as offices in Vancouver, UK, and representatives in Paris, France, and Moscow. And I believe Micon's probably done at least 800 projects worldwide. The other shareholding company of M.Plan is the Dorfner group of companies. They were been in the business in both specialty and industrial minerals for in excess of 100 years. So they're family owned and they're independent. And as part of the Dorfner group, they formed Dorfner ANZAPLAN some 30 years ago. And Dorfner ANZAPLAN provides analytical services, process development and engineering services. So any test work or pilot plant for specialty mineral metals and high value industrial minerals, that's obviously the place to go. As M.Plan, we are experts and our focus is on the specialties. Drawing on 30 years of service between both our shareholding companies, Micon and ANZAPLAN. And in terms of our typical clients, of course, they're mining companies for the study side, financial institution and investors, trading houses, specifically usually looking for offtakes, as well as chemical and automotive industry when it comes to educating and doing any due diligence on projects. And if we look at the commodities that we do look at within the space, the typical ones are lithium, cobalt, nickel, graphite, scandium and rare earths, vanadium, high purity alumina, high purity quartz, just to name a few. So let's jump into it. So let's start with the lithium outlook. Before I just narrow on lithium, it's probably worth mentioning this, and I've brought this up in my prior presentations. You know, within the wider group of specialty mineral and metals, it's not just for the metallurgical properties, but it's also for the non-metallurgical properties, such as particle morphology, crystal structure, color, particle size, or surface properties. And you can see on the right side, this is a nice mineral, a lithium spodumene mineral. You can see the large coarse grains. And so just to talk about some of the applications out there within these specialty mineral metals, of course, we have lithium, nickel, and cobalt chemicals used in battery applications, vanadium used in energy storage, quartz and semiconductor applications, high purity alumina used in bioceramics, but it also can be used in lithium-ion batteries as I guess as a new material that people are looking at. Rare earths used as LEDs and high-performance magnets, silicon used in wafers and solar panels at extremely high purities, scandium, niobium, vanadium, all used as alloying elements in specialty steels. Rare earths used in smartphones and tablet PCs. Expandable graphite as a fire retardant. Diatomite used as a filtering aid, and you couldn't have beer without diatomite to get all those fine particles out. Clay minerals and modern pharmaceuticals, as well as feldspar as fillers and paint, plastics and rubber. So quite a wide range within this group of what we call specialty minerals and metals, and each have unique process routes. So if we now talk, you know, focusing more on the battery raw materials, and when it comes to, you know, specifically electric vehicles, it's the chemical, automotive, and high technology end use markets that are really driving the need for mining projects as well as process development. And what I'll say is, I'm starting on this slide, but this is also my last slide. And it's probably worthwhile just to jump out and mention you know, some of the more interesting points here right at the start. You know, we can see there's a nice picture here of, you know, Tesla Gigafactory in Nevada, which is really, you know, the starting point of all this talk of mega factories back in 2014. And whereas today we have 70 battery mega factories that are either active or under construction. And so what does this mean to the mining industry? There's an estimate that, you know, in terms of investment needed is anywhere from 30 to 45 billion when it comes to projects. And obviously there's significant growth ahead. Just looking at the chart on the right in terms of the forecast demand growth from electric vehicles between effectively now and 2030, we have nickel at 14 times growth. And this is not global nickel, this is nickel that's directed specifically towards for use in electric vehicles. Graphite 10 times, lithium 9 times, cobalt 3 times, and manganese 3 times. So quite significant growth rates when we compare them to, for example, if you looked at copper, globally it ticks along at the, you know, the GDP rate, global GDP rate, let's say, you know, 3% or somewhere around there. Well, these are growing significantly at higher rates, which is why it's an exciting sector to be in. And what's, you know, what is the basis for all this interest in all these battery raw materials? And it really started from all this increasing regulation and policy out there. You know, good support from either regional or country-specific climate change and clean energy policies. And the automotive sector is moving to these low carbon options and obviously moving to higher fuel efficiencies. And most of these policies include either a reduction or a ban on the sales of internal combustion engine vehicles or, you know, ICE vehicles. And most of that is focused in the time period between 2030 and 2040. It's hard even to keep the slide updated. You could look in the UK, there was an announcement that just came out that the UK is now moving, instead of 2040, they want to ban you know, it's petrol and gasoline vehicles by 2030. If we, you know, look at Canada, where we're located here, headquartered out of M.Plan, you know, there's a ban on ICE vehicles for 2040, and in fact, the province of Quebec in Canada just announced that they're going to be ahead of that, and they're going to put a ban on ICE vehicle, new sales of ICE vehicles for 2035, which is great in terms of stimulating, you know, in terms of the projects within Quebec, and is specifically good for the supply chain in North America. And if we look further in North America, specifically in the US, this just also came out. 28 companies launched what they call the Zero Emission Transportation Association, or ZETA. And their goal, and you can see here's some of the companies listed. A lot of them are well known to us, where they target 100% of vehicle sales for light, medium, and heavy duty cars, which are more of the commercial cars, a segment of the market, by 2030. So again, moving away from a lot of these 2040 targets. And so this is great to see and positive for the industry, because obviously people working towards much tighter timeframes, which will help with adoption of electric vehicles. So looking at some of the charts, look, there's many different analysts with lots of different models. So I just have a snapshot of some of that. But the reason for the growth that we're seeing is really based on the commitment of both the chemical and the automotive manufacturers out there. And so if we look at globally today, we're somewhere around 2 million vehicles that are under electric vehicles in terms of passenger vehicles, and now that's predicted to move to 140 million by 2030. And the chart on the right shows you this split out based on the region, based on the percentage, and we could see that China and Europe combined by 2030 represent about 72% of all electric vehicle sales. So this is quite significant. And these are the two main areas that get a lot of attention out there. Of course, when it comes to US and North America, they are quickly organizing, and I have no doubt that there will be catch up in terms of the announcements that we're already starting to see out there. If we look about the mix in terms of those passenger vehicle sales, based on whether it's internal combustion engine versus the electric vehicles, we've really peaked when it comes to internal combustion sales. The highest its forecast was in the past in 2017, as we see steady growth in electric vehicles, as you see in both of these charts. And so it's quite significant from where we are. And I believe the adoption rates in electric vehicles is somewhere between 2 and 3% right now, and obviously forecasted to increase steadily over time. So it's not just passenger vehicles. There are other market segments that it's worth mentioning. We do have electric buses. And in a lot of other countries, there's a lot of 2-wheel or 3-wheel vehicles. It could be scooters or other motorbikes or other type of vehicles. And those, in fact, have higher adoption rates already in terms of a move to electric. So I've included that. So that's again, it's not just all about passenger vehicles. There's many different segments out there. When it comes to the commitment in terms of automotive sector and in terms of investment, it's been estimated there's a commitment of about 300 billion out there across all of the leading automotive companies. And I'm sure this number, is always changing based on, the everyday announcements that we see. It's hard to actually keep up, but it's quite significant. And Volkswagen alone has committed to approximately 91 billion in terms of its investments in the EV sector. Now, here's a chart from S&P Global, and everything initially was all about China. That was the core of where all these future development is. But Europe has really caught up, and you can see in 2019, in terms of investment in the supply chain for batteries, Europe's made significant headway, and this chart was made around June of 2020. So up to the middle of 2020, Europe still continued to beat China in terms of investment in this sector, and so that's great in terms of sort of the global balance out there. It's not only about China and Asia. There is a rebalancing of supply chains, and we've seen a lot of companies talk about those forecasts about that rebalancing of supply chains. So here we have, if we talk specifically about the mega factories, which are, the numbers are always changing, but 2014 we started with just 2, and prior to that, no one was talking about, mega factory. No one knew what these things were. And now every day, I think I don't see a headline in LinkedIn or even in the media that doesn't include the mention of the word mega factory. And as I mentioned in the opening slide, we have today, we're around 70 mega factories that are either active or under construction in 2020. And it's been announced that there's about 168 mega factories planned to be in production by 2029. So this number is probably already wrong. It's probably already out of date. It's probably a bigger number by now, based on, again, all these constant announcements. But that's to show the resolve and the strength and the commitment from both the chemical and automotive sector. As I mentioned also at the open, a lot of this started by government-driven initiatives. So it's not just climate change policy, but we also have other influences like the European Green Deal, where they've, I believe, pledged in at least $1 trillion to tackle climate change. We have the EU critical raw material list that came out in September of 2020. The US had its own critical material list a few years ago. Even Australia came out with its list recently in 2020. We had a US executive order in September where they were talking about their own strengthening their own supply chain specifically against China. We're seeing a lot more regional interest and strengthening, and this is only good for mining projects from that perspective. And here's well, I'll call it a spaghetti diagram from the European Union, from their strategy report from their 2020 critical raw material list. And here they identified rare earths, for example, having the highest supply risk. But if we look at other commodities that we follow, scandium is a high risk, graphite, cobalt, moderate risks. And in fact, the European Union specifically spoke to lithium, and they said that they wanted to get 80% of all domestic supply in Europe of lithium based by 2025. This is certainly aggressive, and most people question that. But you know what? Let them set that policy. Let them set those targets, because it's actually affected our business, I could say, as consultants, because we've seen a lot of interest in terms of people wanting project development or process development and having access to Europe for funding. So it's changed the way projects are reacting to Europe. So that's been, good on them for doing that, but we've definitely seen change as a result of these announcements in terms of our business. And one of the other key drivers is also the cost of a battery pack when it comes to lithium-ion batteries. So, there's a lot of debate. What are the actual numbers out there? I saw this chart just the other day, so I've included it in the presentation. And we've had significant reductions in the costs, over the last few years in terms of where they were forecast to be. And the point being that we're near this $100, but they, where they're trying to achieve parity with the internal combustion engine vehicles. And so we are somewhere near that now, and people are continuing to forecast that it will go down further. The only caution I will say is if we see increases in prices and commodity prices, will it be easy to sustain these downward trajectories as shown in the slide? I would say this is probably a little bit optimistic. Because raw material costs will have some influence, but the positive news is we are at the tipping point where it can allow the cost structure to be competitive, which is an important part of it. It's not just all about government policy. And so now if we zero in more specifically on lithium, here's actually a nice chart actually by RK Equity. And in fact, you can see the forecast demand split by both lithium carbonate and lithium hydroxide. And we can see where we are around 2020, somewhere around demand being 200,000 tons a year, where the majority of that is in carbonate, but in the future, we'll see an increase in terms of growth rates, in terms of lithium hydroxide, which is more suited probably towards the batteries with the more prevalent or say new technology batteries like the 811 and things like that, NCM 811. So, but it also shows you that when it comes to projects, there's a lot of room for lithium carbonate and lithium hydroxide projects in general. It's not one is so dominant than the other from that perspective. Looking at the market balance between lithium chemicals out there, between hydroxide and carbonate. Here's a slide that was I have to thank Roscoe for providing that to this webinar. And in fact, we can see that there's excess material right now in the market. We're in surplus when it comes to refined lithium, but it's going to tighten significantly in 2022 and 2023. And in fact, they're forecasting that the market will be in deficit starting in 2024. And I guess this makes sense in the sense that there is definitely an underinvestment when it comes to lithium projects. And in fact, if we go to 2030, we can see the solid blue line is their base case, where they're saying, there's going to be investment needed. And here they've identified 390,000 tons of LCE, which is the equivalent amount units of lithium needed. This is easily, if we look at the typical footprint of a project being 25,000 tons, you need at least 16 projects just to fill that space going forward. And if we think it takes, a mining project takes somewhere between 7 to 10 years to go through the development stages to production, we're talking like now. You need the projects now in the pipeline. So that's quite significant. And even when the market goes to deficit, as we add units, some of the projects will not meet the quality needed out there. So that's another constraint that's adding to why there's such forecast deficits in the future. Also, it's worth mentioning, prices obviously have an effect on the investor sentiment. And so in the period of time between 2017-18, we had increasing lithium prices as well as other commodity prices related to battery raw materials. And in that period, we saw a lot of interest from investors. But in the last, since 2018, we've seen a decline in lithium prices. And so that's put some of the investors on the sideline while they sort of wait to see what happens. But prices do have an impact on investor sentiment, and there is a view that with a tightening in terms of supply and us moving to deficits with the lack of investment, people are predicting that we're going to see higher prices across the board. And in fact, we've seen Altura, having some issues in terms of move to care and maintenance from that perspective. So that's even taking away spodumene concentrate off the market in the short term while they, sort that out. So, so the price will definitely have an impact. And this means when it comes to projects, differentiating projects from one another in terms of having robust projects will also be important on the cycle forward. And this is why it's worthwhile to now sort of say, how does this actually affect projects from what I've stated? And I've brought this up in the other webinars, and it's worth mentioning here again. If we contrast to precious metal and base metal projects, the development is much more linear. They follow that linear development path. Test work follows after significant exploration and drilling, and a lot of end-use markets are assumed. If you're a copper project in Chile, you can look at your neighbors, you can look at if you have similar mineralogy, and you can pretty much, I want to say guess, but you could look at what processes they are using to guide you as what would be likely for your project, but it's not the same when it comes to specialty projects, specialty minerals and metals. They are much more iterative and require much more robust, use of test work and process development and as an iterative step. And it starts with initially, looking at the end use application. So lithium, there's not just one market, there's different market segments. And so, you're going to have to look at those applications in terms of making sure you can establish potential economic value in the project. That early test work evaluates the potential markets, and as well, you need to understand, can you potentially achieve that product specification, whether it's carbonate or hydroxide. And then this in turn helps define your exploration strategy and targets. But then you're going to go back and further refine test work, you know, in terms of looking at your potential process flow sheets, costs, and economics from that point of view. The other thing worth mentioning when it comes to projects, it's not just about purity. And here's a chart on the left where we've sort of shown typical specifications for lithium carbonate and hydroxide. And of course, we need to achieve very high purities in the case of lithium carbonate, 99.5 as an example. And it doesn't leave you a lot of room to maneuver, because that leaves you with 0.5% of impurities. And impurities matter. They make a big difference when it comes to OPEX and CAPEX and projects. You know, if we look at iron, you're limited to here only 10 ppm in carbonate and, you know, 5 ppm in hydroxide. So, you know, you could easily go over and not achieve the purity, or you could be downgraded even though you achieve the lithium component. It's the other ones that matter, and that's why it comes down to your process. There are obviously different minerals when it comes to lithium. The one that we talk about most often, we see written about, is probably spodumene, the most well-known. And in this case, you know your mineralogy, know your processes. There are different economic paths for different minerals, but some of the other ones that we do see is petalite, lepidolite. Lithium clays have been in the media, obviously. You know, Tesla's helped raise the awareness, as well as you know, lithium vitric tuff as another one, for example, in Peru. So there's many different forms out there, and they all have potential for, you know, potential economic value in terms of making what makes a project. And so it's worth mentioning another influence, you know, Tesla Battery Day. We can't stop talking about it. We can't stop talking about their interest in lithium clays in Nevada. So in fact, we're going to hear a little bit about that today from both Dr. Prinz and Dr. Graf, who will tell us a little bit more about that. So we've tried to bring something more interesting to the table from that perspective. When it comes to lithium deposits, here I've shown them by size in terms of their resource, reserve size for operating and projects. And so again, as I mentioned, it's not all about lithium spodumene. If we look at, again, the different projects, we've got clays in here, the dark blue, you know, spodumene projects, which may contain petalite, or as well as lepidolite. You know, there's micas, as well as other ones like jardarite, as well as tuff. So, you know, again, there's room for everyone to compete in this market in terms of, you know, different potentials. And obviously it's based on region and other inputs into these projects. So as I said, I started with this slide, and I'm coming back to this to close my section of the presentation. But obviously, when it comes to lithium as well as other battery raw materials, you know, there is definitely significant growth ahead. It almost seems hard to keep up with all the announcements, but the model has changed out there. A few years ago, it was more about these forecast electric vehicle, demand out there, and people weren't really sure if it was real. But now we're in a period where there is no question, it is here, it has arrived. And now, again, on the technical side, you need your experts when it comes to projects. And with that, I'll turn it over to Dr. Sebastian Prinz, who will lead us off in lithium mineralization. So we'll give Sebastian a moment here to get his camera and switching screens.
Thank you so much for the introduction, David. And it was very interesting, I think, to see those exciting perspectives of the industry. So that was very encouraging, I think, for everybody in the field. So first of all, I'd like to start by giving you a short introduction to myself. So my name is Dr. Sebastian Prinz. I'm a mineralogist by training with more than 15 years of experience in this field. I joined ANZAPLAN in 2011. As the director of the business development at ANZAPLAN, my focus is on specialty and high-value industrial minerals and metals, such as, for example, the lithium that we're talking about now, the REE, graphite, and other specialties. My field of expertise is the genesis of ore deposits. I also have a very good understanding of the characterization and the properties of mineral and deposits in those fields of the specialties, as well as all the market aspects associated. So with this, I would like to start my presentation. It's going to be about lithium mineralization. So I think David already showed you these different kinds of minerals that are out there for lithium. In total, there's more than 140 different lithium minerals which are known. The most important ones are shown here. So you can see spodumene having a slightly greenish tint here, which points to the fact that it contains some iron in its lattice. Then there's petalite, fairly whitish here, usually also lower in iron. Then what is on the right-hand side, you can see the lepidolite, which is a lilac mineral. It's a sheet mineral or a mica. Then you find below the lithium clays. Lithium clays are very interesting. There's different kinds of clays with different properties, and lithium also plays different roles in them. Then there's a vitric tuff, David mentioned it, and a zinwaldite. So going a bit further into those structures, and that's what's really I'm interested in. So you can see spodumene. I tried to depict with the colors which are reflected in the structures shown in the mineral structures. So what you can see for spodumene, it's basically a chain structure with tetrahedral chains of silicon and octahedral chains of aluminum. And in between the chains, you find the lithium. It has a fairly high lithium oxide content of 8%. And the typical Li2O grades are from 4 to 7.5 for the commercial concentrates that are sold. Then there's a petalite. It has a very different structure. It's basically a silica sheet structure, which is linked by tetrahedral lithium and aluminum, making it a three-dimensional structure. As I said, it's usually lower in iron contents, and the lithium grade is as well a bit lower, for around 4.9%. Both spodumene and petalite occur in pegmatites. Then let's switch to another structure of lithium minerals. There are the micas. The most prominent ones and the most talked about ones are lepidolite and zinwaldite. Lepidolite is typical of pegmatite setting, which can display quite high lithium oxide contents of 7.6% up to. The grades in the concentrates are between 3 and 4.5%. Zinwaldite, as opposed to the lepidolite, can also contain some iron. So I did not really talk about the structure too much, just to briefly mention it here. It's a tetrahedral, octahedral, tetrahedral setup. And the lithium, in both cases, you would find in the octahedron, replacing for some of iron or aluminum. Then there is also, as a clay mineral, the hectorite. It is deposited in a sedimentary setting, and it shows a similar also layer type structure of tetrahedral, octahedral, tetrahedron. And in between those layers, you find some balancing sodium and water as well. With hectorite, the lithium is also in the octahedra. But then there's other clay minerals. I think Dr. Graf will talk about this also later on, where it may be differently. For example, in montmorillonite, you find lithium in between those layers, where we now can see the sodium. So how does lithium get concentrated? Lithium is really a very tiny thing, and it's incompatible. or hardly compatible, which means it doesn't readily go into common rock-forming minerals. It belongs to the group of alkali metals, and it's basically concentrated by plate tectonics. So the main processes that are taking effect is partial melting of the rocks on the one hand, and also differentiation and fractionation of fluid-rich fertile magmas. So the concentrations are shown here on the right-hand side. Maybe you wonder, why is lithium not more abundant in the ocean? It's just below 1 ppm of lithium content there. Researchers believe this is due to the case that the deep sea clays are actually scavenging the lithium, which is why they are fairly rich in lithium with around 57 ppm. So one of the main types of hard rock deposits are LCT pegmatites. They are found in metamorphic settings, so in the hinterland of orogenic belts. They are formed by a high degree of melt fractionation. And the most important prerequisite is that you have a fertile granite, which means it's a metal-bearing granite. And this high degree of fractionation then results in a strong enrichment of lithium, cesium, rubidium, and tantalum. And due to the presence also of flux in those melts, such as fluorine, phosphorus, and boron, the viscosity of those melts is greatly reduced, and which makes them very mobile. And that is why they form those kind of dikes and cells that you can see on the right-hand side, and which are usually fairly irregular. What is a very prominent feature in pegmatites, of course, is the coarse crystallinity, which is also caused by the flux being present, as it will reduce the number of nuclei in the melt, and therefore just suppress the formation of a lot of crystals, but just a few very coarse ones. Usually the size of those deposits is fairly limited, so up to several kilometers in length, hundreds of meters in width. Main lithium pay minerals I already mentioned in this kind of setting are spodumene, petalite, and lepidolite. A second type of deposit also related to large granitic bodies are Greisen type deposits. They usually form, as you can see on the right-hand side, in the upper part of those granite bodies, and there's very, very large deposits in Europe present. And as a company, we're also working on such type of deposit presently, quite intensely. And these deposits are formed from magmatic hydrothermal fluids, which basically stream through the upper parts of these bodies, mineralizing them. The composition is similar to what we've seen for the pegmatites. Also, they are containing lithium, boron, and fluorine typically. The formation temperature is quite a bit lower than with the pegmatites, though. In terms of the shape that they form, they can be observed to form large and sheet-like intrusions of fairly large areal extent, so it can go up to tens of kilometers. And this mineralization is fairly pervasive, so it means that you form rather fine minerals, which include also the tin and tungsten minerals, cassiterite and scheelite. But of course, what we are interested in right now, it forms lithium mica zinnwaldite, as well as some topaz, tourmaline, and fluorite, which takes up those fluxes being present in the melt. So a final very different setting that I would like to showcase here to you is sedimentary deposits. These can be lithium clays or tuffs. The typical setting that they are found in is a closed basin setting in arid environments formed by extensional tectonics a very good example for such a setting is the Basin and Range province in the US. The clay deposits are formed by sedimentation of fine-grained clastics, for example, volcanic ash. An example is shown here on the right hand. You can see that little volcano there. And they are closely related also to lithium and magnesium enriched brines in such basins where they settle. And often you also have some hydrothermal fluids, which are again rich in fluorine and lithium, which can alter then those sediments that have been deposited in such a basin. And this could be andesites, carbonates, or volcanic tuffs. And by this alteration, they are transformed into clay minerals, for example, such as hectorite and montmorillonite, but there's a wealth of different other ones. And so what in this type of setting is also very important to note is that you would usually have a mix of different clay minerals, which also have very different properties, as I tried to showcase with hectorite and montmorillonite already. And then you've got some other evaporites, such as gypsum and carbonates or halides, in different proportions, and this is of course very specific to each and every deposit. So this has very important implications for the processing, which then needs to be tailored to address those different minerals and to finally come to a processing that can successfully extract the lithium. So yeah, I think this gives you quite a nice overview now of the lithium deposits, and I would like to hand over to Dr. Christian Graf, who will give you some more insights on the processing side.
Thank you very much, Sebastian, for a nice presentation and nice outlook. Could you see my screen?
Yeah.
Perfect. So I would like to proceed here and talk on lithium processing, but to briefly introduce myself, my name is Christian Graf. I work for ANZAPLAN as a process division director for 3 years. Prior to this, I had product manager as well as business development manager positions in 2 major lithium companies, namely Rockwood Lithium and Albemarle. And prior to this, I worked in the chemical industry supplying precursors for lithium-ion battery materials to the world. And now I want to tell you a little bit how the lithium comes out of the earth and goes into the battery. As Sebastian or Dr. Prinz just mentioned, there are basically 2 major sources of lithium on the planet. One is brines and the other one is ores. I would also include the sedimentary deposits in the later category. From the brines, a lithium carbonate could be produced pretty easily, and this is done from Livent. This is done by SQM as well as from Albemarle, and mostly in the lithium triangle in Southern America. From ores, you could also produce a lithium carbonate pretty easily, as well as you have the option to directly produce a lithium hydroxide. The lithium carbonate basically forms the root of the lithium tree, so most of the lithium chemicals needed on the market besides of battery applications could be derived out of lithium carbonate, and lithium hydroxide gains importance in the new battery field. To really go with the flow sheet, and I promise you will see quite some flow sheets today, I would like to start with the first steps, which is the mineral processing from this. So on the right hand side, you see a chart where I just took the categories, so spodumene, petalite, micas, which includes lepidolite as well as symboldite, and on the right hand side you have the lithium clays that I also want to talk on. So these minerals really differ themselves from their head grade, where you see the spodumene and petalite are typically in the same region, followed by mica and then by clay. On that crystalline deposits, you typically need a crushing step first, which is done by a jaw crusher, and this is not required in a lithium clay setting. On the coarse crystallites, namely spodumene and petalite, which are formed in the pegmatites. Pre-concentration methods such as ore sorting or DMS are possible in coarse grain fractions, and these offer fantastic opportunities to increase the grade and even bring you up to a sellable product, which is done by a couple of projects around the world. And based on the mineralogy, these are not possible for the micas as well as for the clay deposits. And then a milling step is required. This milling step is either required for further processing steps, such as in spodumene, petalite, or mica, or for the subsequent hydrometallurgical steps, which is then true for the clays. Typically, after that milling step, a magnetic separation is involved. Typically, for the pegmatitic minerals, this is used to remove some ferrous impurities or other magnetic impurities. This could be done for lepidolite too. And for mica, you have the opportunity, because the mica, the synwaldite, has some iron in the lithium-bearing structure, to really enrich the pay mineral using magnetic separation, and therefore bring you forward with a pretty easy and elegant flow sheet there. One of the main processes in lithium ore processing is the flotation, which is pretty common and also widely known. For the micas, which are typically handled first in sequence, it is pretty easy and straightforward, and also well established for spodumene. When it comes down to petalite, the flotation sequence is pretty complex. First of all, because petalite is taken out last in that sequence, and also the conditions for the petalite flotations are tricky to handle, but are well known, and experts in the market could really bring you forward with your petalite flotation. I just recognized that I really talk about very last on the lithium clays, and therefore I want to go into a brief introduction to the lithium clays. Here's a picture you saw from Dr. Prinz already in a little bit smaller form to talk about the structure of the lithium clays. Here in this case, I want to really go more into detail and talk about the atoms and where the atoms are located. So there are basically two categories of clays. One is a swelling and one is a non-swelling clay. But this doesn't play a role, because if you look into montmorillonite and hectorite, both are swelling clays, but both have clays on different sites. Whereas for the hectorite, the clay is really sitting in the octahedral environment here, indicated by the green octahedra, whereas on the montmorillonite, the lithium sits into interlayers, represented by the pink circles in the middle, surrounded by water atoms. So both of these clays are found in clay deposits, and the occurrence differ a little bit from the deposit where it's made from. So because of the different nature where the lithium is located, there's a variety of methods which you can use to extract the lithium. So first of all, there's the sodium chloride leach. So please remember Elon Musk talking about you take a little bit of table salt, sprinkle it on your clay, and the lithium comes out. We did this experiments as well. These are well known to the industry when it comes to clays. And we also did quite an extensive testing on other clays. So I really want to thank my colleagues on that and providing me the data in really good time. And what does it show? Or what do we did? So we take Clayton Valley clay, where we know that the lithium sits in the interlayers. So please remember the pink circle from the prior picture. And we took a Clayton Valley clay where we know that the lithium sits in the lattice. Please remember the green octahedron. And then we took a hectorite where we know that the lithium sits in the octahedron. So we tried the cation exchange, and it worked well for the Clayton Valley deposit, and also other methods such as sulfuric acid leach work, sodium chloride bake. So there's also an option for sodium chloride at high temperatures, and a sodium sulfate bake worked all well. If it is located in the lattice, the lithium ion, the cation exchange, so the sodium chloride method, don't work. So maybe to be a little bit more familiar, we brought it to metrics, and to say it pretty easily, the sodium chloride leach just works for materials where the lithium sits in the interlayers. So these materials are known to occur in the Clayton Valley. But also in the Clayton Valley, there exist materials where the lithium is not in the interlayers. But you still have the option to work with an acid-free environment, such as a sodium sulfate or a sodium chloride bake. Because of the temperature, of the higher temperature, the sodium sulfate bake and other restrictions is preferred. These work also for the hectorite too, so also for other lithium-bearing clays. So there's a variety of methods for lithium clays and to get lithium out of these clays. And there are also acid-free environments, acid-free methods based on this. But now I want to go to other routes. I want to go back really to the minerals and tell you a little bit more about the processing, the hydromet processing of these minerals. So as we just outlined, as David Anonychuk as well as Dr. Sebastian Prinz did, we have these three categories, so spodumene, petalite, mica, and clay. And when it comes to leaching, these differ quite a bit, whereas the left-hand side, the pegmatitic minerals, really need a calcination step followed by an acid baking step. On the right-hand side, so the sheet aluminum silicates really could be treated with a thermal caustic roast or cation exchange. And after these steps, all of these minerals and materials will be leached with water, and it will yield you a sulfatic PLS, so pregnant liquor solution containing lithium. So the lithium species in this is a lithium sulfate. And then you really go into processing because you want to bring it to battery grade quality, and therefore you have to remove impurities. So what are the key impurities to remove? These key impurities are iron, aluminum, magnesium, and manganese. So a key step on this is a line addition, where most of these elements are separated as a hydroxide that will be filtered off. After this, calcium will be removed as a carbonate, and therefore soda ash will be added in minimal quantities. You will do a solid liquid separation and a polish filtration after this, and do an ion exchange to really bring down the impurity levels of the mentioned elements to single digit or even below that ppm range. Please keep in mind that what I just say here and the flow sheet that I depicted is very rough and very high level, because the impurity removal really have to be matched to the specific elements that needs to be removed, and that were introduced with the specific concentrate as well as with the different minerals, namely boron, fluorine, as well as potassium, which could be introduced with mica, which could be introduced with a clay deposit. So these have to be handled. There are technologies available, we know on them, and we apply them on a regular basis. And then you really come to the carbonate processing. If you want to process the carbonate, you will add some soda ash on the beginning, do the exchange with the lithium sulfate. Sodium sulfate will be formed under lithium carbonate. That lithium carbonate is hardly soluble, so it really forms a precipitate. That precipitate will be filtered off and washed. And if you analyze this, this will not this lithium carbonate will not meet your battery grade specifications. So it's typically rich in sodium as well as in sulfate. So it needs to be further purified, and that this purification is done with CO2. So soluble lithium bicarbonate will be formed. Unsoluble impurities will be filtered off, and then the lithium bicarbonate solution that is purified will be heat treated, and lithium carbonate will be formed, filtered off, and these materials are typically of battery grade quality. But what is the story with lithium hydroxide? So I just want to show you two pictures. You have lithium hydroxide on the left-hand side with a 200-fold magnification, and then lithium carbonate with 3,000-fold magnification on the right-hand side. So you see really a difference in the materials. So lithium hydroxide forms large crystals, whereas lithium carbonate forms really small fragmented co-crystallites. And this is really coming from the different solubilities. So lithium hydroxide has a much higher solubility than lithium carbonate, and this also has to be respected in the respective flow sheets. And therefore, and also, I'm a little bit too fast here, but there's also another difference which you have to respect in the different flow sheets. So the specification of the lithium hydroxide is much more stringent than for lithium carbonate. If you look at the sodium values, they are much lower. The iron values are lower, the chloride as well as the sulfate values. And there's also a major impurity in the lithium hydroxide, which is CO2. So, and this really comes from uptake from environmental air. And so you also have to respect the CO2 contamination in your flow sheet. And so let's come into the flow sheet, and so I will show you how lithium hydroxide is then being produced. So you can take the same liquor coming from an ion exchange that you took for lithium carbonate production. In this case, you will add a sodium hydroxide. So you do an anion exchange on this, and you will form sodium sulfate as well as lithium hydroxide. As both of these compounds are pretty well soluble, you have to really get the sodium sulfate out of this, and you do this via cooling crystallization, where chloride salt will be formed, which is a dodecahydrate of the sodium sulfate. And with the chloride salt, the majority of the sodium impurities will be removed. And after these sodium impurities are removed, you can start with an evaporative crystallization to start to crystallize the lithium hydroxide. Crystals will be formed then, will be filtered off, and the mother liquor will be refeeded. After the filtered off crystals, they typically weren't analyzed, but if you would analyze them, they would not even close to fulfill that spec. So these crystals need to be recrystallized, and therefore they will be brought back into solution with minimal amounts of water, and a recrystallization step will occur where the majority of the impurity stays in solution and will be refeed either to impurity treatment or to prior treatment steps. And also, out of this treatment, sodium and potassium needs to be plated out. There, the final product needs to be carefully tried and packaged and sent to the customer. But there's also another option available, which is also done commercially. If you think about Livent, if you think about Albemarle, they produce the lithium carbonate down in Southern America, Argentina, or in Chile, and they will produce their lithium hydroxide in the US, and they do this via a metathesis reaction. So lithium carbonate will be reacted in a solution with water. with lime. So ion exchange will occur where calcium carbonate is formed and lithium hydroxide stays in solution. The lithium carbonate will be filtered off, and the lithium hydroxide precipitation will occur, which is pretty similar to what I described before. So it's an evaporative crystallization where on the first stage crude lithium hydroxide will form based on customer specification. How well is your lithium, how well in spec is your feed lithium carbonate, and also how the process is set up. Maybe a secondary crystallization stage is needed to bring this up to a lithium hydroxide. And also in this case, as in most crystallization streams, need to be added to really remove impurities there. I think that wasn't too much of text speech and too much of flow sheets for you. If there aren't, please feel free to type any questions in the box below. So thank you very much for your attention, and yeah, I'm happy to hear your questions.
Well, thank you for that, for Christian. And so I'd like to thank our experts today, Dr. Sebastian Prinz and Dr. Christian Graf, for joining me today. Your time is very much appreciated. So yeah, I know we've completed the full hour, but if everyone is happy to stay on the line, we're happy to answer any questions that you have. There is one. So for Sebastian, just to start off, we can see that depending on where the lithium is in the minerals, for example, all clays are not the same. And I can say, listening to other projects at some of the other webinars that we've heard recently, they've all said our project is different. And so that was, I think, loud and clear from both actually your presentations. So Sebastian, I guess the question is, what is the value of mineralogy up front, even before you do your process test work? And what would you, and when you look at mineralogical studies, what do you typically do for a client when it comes to that? So if you could maybe just explain that for us.
Yes, thank you, David, for that question. I think it's very valuable to give some comments on what mineralogy or mineralogical analysis can do there. So one of the things that we usually do is X-ray diffraction, and this would help us to define the mineral phases that are present on the one hand, and also to quantify them. And it's a fairly convenient method. It's non-destructive, and it would give you very accurately what you have as a content of mineral phases. And then secondly, there's also SEM, so scanning electron microscopy. This helps us in determining if there's intergrowth, for example, in spodumene, which is typically intergrown with quartz, the so-called SQUI. This would then give us some information about what the size of the intergrowth is, and what the actual grind size should be to liberate those minerals. Because then MLA could be performed to see whether in the processing the lithium minerals have been liberated to the extent they should be liberated in order to make them amenable to further concentration and finally the lithium extraction. So those are all very valuable methods when actually determining how to best process your material.
And yeah, thanks for that, Sebastian. I know from experience on projects we've worked on together, where some clients at the early phase, when they're looking at outcrops of deposits in terms of lithium, they're not necessarily sure what's in them. They may, we've been approached to say, oh, we believe it's majority spodumene mineral, but when we've received those samples and through that analysis, sometimes we say, oh, well, actually, you may have petalite or you may have lepidolite in there. And so those are all important considerations when it comes to understanding your deposits, again, specifically at that early stage. So again, thanks for that, Sebastian. Christian, question, for yourself, I have to go back to the clays. That's one of the things, again, that I think was really good for the industry in terms of lithium, bringing more attention. So was Tesla right when they said, you know, just sodium chloride and they can extract, you know, minerals? So now that you've had a chance to, both of you, to talk about clays, you know, was he right?
Easy answer, yes. Long answer, no. Easy answer, as we demonstrated, it's really possible to sprinkle a little bit of table salt on a clay and get lithium out of this. With the long answer, it was probably overly simplified. You need typically large amount of sodium chloride to do a cation exchange. What you also have to keep in mind, if you sprinkle sodium chloride on a clay and want to backfill this, you still have large amount of soluble chlorides in your clay, which probably give you environmental headaches. It was demonstrated, we demonstrated that sodium chloride at high temperatures really also get you lattice lithium out of this. So this is then true, but you really have to look very careful if your clay that you have in your deposit is suitable for a cation exchange, or isn't there another method even more economic or environmentally friendly than this method?
Great. No, thanks for that. And question on lithium conversion plants. So we're starting to hear more interest from energy and petrochemical companies being interested in entering this phase as they look at their long-term strategy. So could you comment, have you seen this develop? But I'll comment, but I'll let you start, Christian. Have you seen a change out there in terms of people's interest to get into that space?
There's definitely a change. There's a change either from large chemical companies that really want to get in the field, that are in the field of alkalis or things like this, that really want to go into lithium. There are other companies that are related to energy that want to get in the field, maybe with different production methods, and because they have a source of clean energy. I think there's a growing interest really in non-chemical, non-lithium companies really to get in this field, because the market, in my opinion, now has a size where it really attracts a lot of large-scale players, not typically related with lithium in the past.
Yeah, no, that's a fair comment, because I think I said we've seen definitely interest out there from companies wanting to evaluate the sector and specifically study, you know, potential to construct plants, lithium conversion plants. So that's a good sentiment or a good measure of interest out there. And I think it also helps all these government initiatives have definitely helped get, you know, change the way that people are looking at the sector. There's let me just go here to some notes. Another question, what will bring investors to the market when it comes to lithium? And I can comment, I mentioned this before, I do believe that prices, based on our experience doing due diligence, prices are definitely one of the leading indicators that get investors' attention. And if they see an upward trend, they want to see how they could participate on those prices from a timing point of view. And I think it's fair to say when it comes to either lithium or even battery raw materials, we definitely seem to be at the bottom of the price cycle from what the analysts are telling us out there, and in terms of the potential shortages ahead of us. So we definitely expect to see more requirements from investors to do due diligence on projects. So I think that's definitely a positive for all of us that participate in the industry. But it goes down to how do you differentiate projects, which goes back to know your experts, make sure your projects are robust. And it goes back to that underlying test work, you know, pilot plant, all of those aspects make or break, you know, projects from that perspective. I have another question. This is, what about specific CO2 footprint of the different processes compared to brine production in terms of CO2 / LCE? So I don't know if any of you gentlemen could comment on that in terms of expertise on that side. I couldn't comment myself, so.
What's the major source of CO2 in the process? That's mainly energy. So there is no general answer, because you really have to look for the specific placement there, how the energy is sourced, how your kiln is fired. Is it a gas kiln? Is it indirect fire? Is it really electrically fired? If you have cheap energy, this is still an option. I think there are methods that are rather CO2 neutral compared to this. What you also have to consider is what is your supply chain there, and what is the CO2 impact on the supply chain. So there is not a generic answer. The answer is you have to look into detail.
No, fair enough. And so just going through some more questions here, and I've got to look close on my screen so I can see it. Regarding brine deposits, which minerals is the lithium leached from, and how do they get into solution? How do you explore for these deposits? Is it cost efficient to extract lithium from geothermal brine deposits, such as there is in the southwest of Germany? So could you comment? I know the focus was on more hard rock and clays today, but is there any comments you guys can make with respect to brines?
Yeah, so for brine deposits, I think I showed this image. So you need a very specific setting to have such a brine deposit to form. So basically what you need to have is that enclosed basin, and there's very, well, I would say limited locations in the world where you could actually find such settings in which those lithium concentrations finally could form by the arid conditions that you have in these areas. So that is restricted. On the other hand, there's also geothermal brines, as you mentioned. In geothermal brines, you usually have way lower contents of the lithium in the brine. So you need some very efficient processes to concentrate the lithium to get to a state where you are already in the usual salars, for example, that you have in South America. So from that perspective, they're fairly low grade, but they might present another opportunity. So maybe Christian can comment on some of the processing implications there.
On the processing implications, I think you have to come forward with a solution to really concentrate the lithium efficient. What you have to consider is that the geothermal brines discuss their range in the range of 60 ppm. Like this, please keep in mind that the salars in South America, so the Clarice Basin salars in South America start from 600 to 1,800. So there's still a gap of a factor of 10 to 20 that needs to be bridged prior to getting to the same quality, which means there's a lot of water that needs to be pumped. I think there are a lot of technologies already under exploration, and it's an approach definitely have to follow, even when it comes to regionalization of supply chains and having geopolitical impact, which will be a source in Germany. But I really can't comment on this because the geothermal aspect still plays into this, and I'm not quite an expert on this.
No, fair enough. Thanks for that. And I have another question here. Do you expect most lithium projects from junior miners in Europe to reach production? And I think it's fair to say, you know, you have to judge each project based on its own merits, based on its own inputs. They all affect, you know, the jurisdiction in terms of its risk. Like we said, the supporting, you know, test work, pilot plant, all of that add to making a project robust in terms of its ability to compete amongst other projects. I think it's positive with all of the incentives in terms of Europe for funding. And we're definitely seeing in the business a move to Europe. So I think that's a positive aspect. But did you gentlemen want to add any more comments to that? Because you're definitely actively involved in European projects?
We are very involved in European projects. We know most of them. This is also one case where we couldn't really comment into detail. What I really want to say, it's pretty hard to say if a project will really go into production. That is really besides of technology and process implication. It's also about how are they connected? How is the financing set up? How are the people act with the financing? And it's pretty hard to judge really from pure technical or pure financial standpoint if that gets into production. So on the other hand side, I currently see a very favorable ecosystem that will be built in Europe to do this. So I think there might be a better chance in Europe for such project to evolve than maybe in Australia, because you also have a different setup. In Australia, looking at the Vara, Altura, Greenbushes, these are mostly concentrate producers, whereas in Europe, these projects are forced really to go into chemical production. But here is really the environment and the mindset for chemical production.
And actually, so let's close with one more question here. And thanks for everyone for hanging in with us. The should chemical and automotive companies invest in mines? And so if we look at the when we do due diligence and with the clients that we've worked for, there's really 4 categories of potential investor, and there's typically the mining fund, which is usually the ones that are most interested in whether it's on an equity basis or a debt basis to invest in the project. We have the trading companies that are usually looking at offtakes, and then as well as they could either be a chemical company or an automotive company. But what I will say is the more further you're removed from the understanding, mining, making a vehicle is a lot different than building a mine from a project development point of view. The risks associated with them are much different. So having that understanding, so if you're making a vehicle and you're building, you're planning ahead 5 to 7 years in terms of the technology, especially with lithium ion batteries. There's a lot of certainty in terms of what they would like to do in terms of their cost inputs. When we're talking about building a mine, there is a certain amount of risk and uncertainty at the time with those different development stages. So there is an education that needs to be done when it comes to educating both the chemical and automotive companies in terms of explaining how mining, projects and as they move into construction are different, especially things like contingency and so forth. And that's why in some ways maybe the trading companies are best placed if they're the ones taking the risk, understanding the pricing. So everyone has a role to play as potential investors in that supply chain. Anyways, with that, I think look, we appreciate everyone's time for hanging around and asking all these questions. I'd like to again thank Dr. Sebastian Prinz and Dr. Christian Graf from Dorfner ANZAPLAN joining me today to talk all about lithium. And if anyone has any questions, feel free to reach out to us. We'll be happy to answer your questions. And as a follow-up, we'll make sure that we will send you out the slides, as well as be a link to the video if anyone wants to review it or share it with anyone else. So with that, I'll call this to a close and look out for other webinars. We'll be definitely targeting other commodities in the future. So thanks, and with that, I'll close. So have a good afternoon or evening, depending on where you are.